this report on October the 18th of 1990. And the conclusion was very simple. 2 sentences. The ad hoc working group has reviewed all available public statements and written materials by Ivan Browning regarding the prediction for a magnitude 6.5 to 7.5 in the New Madrid region on December 2nd, 3rd. The working group concludes that the prediction does not have any scientific validity. Okay, so they put out a very clear statement that there was no scientific basis to believe this statement. Okay. However, the news media still talked about it a lot. There were all kinds of things. This was my favorite because somebody started to try and monetize the prediction. So for $39, you could buy a videotape where Ivan Browning explains the basis for his prediction and what you should do in order to be ready for this earthquake. So there was quite a frenzy that was created by this whole process. So as the day in question approached, what happened? Well, parents demanded that the schools close. And the reason for that being that the school buildings had not been constructed to withstand earthquake shaking. Frankly, I think that's a very smart thing to do. If there's serious concern, even if there's no scientific basis for it, if there's serious concern about an earthquake in a particular time window, then absolutely let's close the schools. Just on the off chance there is some kind of event. If you close the school for a few days, perhaps that's not the end of the world. But if you don't, and then there is an event, you can imagine the outcome of that. So closing the school is very smart. Shops sold out of flashlights, sleeping bags, canned food, batteries, and booze. Clearly this was an extended holiday for people over the course of the 3 or 4 days, a long weekend, running up to this Monday. Again, perhaps that's not so bad, right? I mean, if that was to happen here, this would just be a great opportunity for everybody to have the earthquake preparedness kits that everybody should have had all along. So maybe that's not too bad an outcome either, frankly. Many people left town. Now we're talking about some serious impacts. So many people left town. Other people camped outside for the weekend. Camping outside for the weekend, that's not too big of an impact, right? So as you can see, we have to start asking ourselves, well, what's the impact of taking an action versus the positive, what you might achieve by taking that outcome, all right? So buying an earthquake preparedness kit, that's probably a good thing. Camping outside for the weekend, probably not that big a deal, right? Just part of a long weekend holiday. But people starting to leave town, that means businesses don't have business. That means people are not showing up for work. There start to be some significant economic impacts of those kinds of actions. So there clearly is a negative impact for people taking that. If it turns out to be an earthquake, well, maybe it's worth it. But if there is no earthquake, then it probably wasn't worth it, okay? The media arrived in town. Needless to say, they were all standing on street corners, interviewing people continuously all day long in the hope that the cameras would be rolling when the earthquake struck. You can imagine the frenzy that this would cause within the news media. And, of course, absolutely nothing happened. Okay? One of the news stories I found about this reported that the biggest impact of this was the traffic jams caused by all the media vans on the street corners of the towns that were affected by this. Okay, so this was an earthquake prediction made by Ivan Browning that was taken seriously by a large cross-section of society. It was obviously completely debunked ahead of time by the scientific community. They couldn't have made a clearer statement in terms of what they were saying was going to happen. So that's the challenge when it comes to earthquake prediction. People get very excited about it, people overreact to it, and to what degree can a scientist actually engage in this process? So let's talk a little bit about his physical mechanism. He did put forward a physical mechanism, which was the reasoning behind it. So what is this sort of earth tide triggering effect that he was alluding to? Well, everybody is familiar with the idea that we have tides, as in water tides, ocean tides, and these are generated by the fact that the moon's gravitational field impacts a significant effect on the oceans at the surface of the Earth, and so you get this bulge of water closer to the moon, and so as the moon rotates around the Earth, this bulge of water moves around the Earth, and that's what causes the ocean tide. Okay? What you probably are not familiar with is the fact that this gravitational effect also has an effect on the solid Earth. Okay? So the effect on the solid Earth, of course, is smaller than the effect on the fluid outer layer of the Earth, but there is a significant effect on the solid Earth. And so this is measuring the vertical movement at the surface of the Earth over a number of days. Okay? And this is in centimeters. Okay? So from trough to peak is from minus 20 centimeters to plus 10 centimeters. The surface of the Earth goes up and down by 30 centimeters, that's this much, twice a day. Okay? Presumably you're all shocked by that. Okay, good, thank you. A little bit of reaction would be appreciated. That's amazing. Okay, I mean, I showed you the effect of the earthquake, the Sumatra earthquake on a seismic station here in California. That was sort of, I think, 3 centimeters, if I remember correctly. In case that was 3 centimeters due to an earthquake on the other side of the planet. Every day, surface of the Earth here goes up and down by 30 centimeters due to the gravitational force of the moon. Of course, it has no impact on us, which is why we don't know about it and why we don't worry about it, because this is obviously very long period motion. We talked about the fact that the earthquake signal is long period. This is even longer period motion. That's why it has no effect on us. But that gives you a sense of just how strong this force is. This is a significant force. There's no question about it. And so the link between tides and earthquakes is that as you're moving the Earth's surface up and down, you are changing the stress regime in the Earth's crust, and that might trigger earthquakes. Okay, so that's the connection. That's the physical model. And specifically, Ivan Browning was saying that all of the planets were aligned, not just the moon, but all of the other planets are aligned, and so this increases the effect. The moon has by far the biggest effect, but if you line up all of the planets, then you're going to increase the effect, and that was what he was pointing to. So what he was referring to in terms of alignment of the planets is that, needless to say, this is not to scale. All of the planets were aligned, and therefore the effect of the moon was enhanced. How often do they line up? Well, it's true that they line up every 179 years. And so what he'd done was said, well, the last big earthquake was in 1811. He adds 179, and that's how you get to 1990 in his earthquake prediction. There is one huge assumption that he made here. Anybody know what it is? No, not December 3rd. Exactly. That all of the planets were, in fact, lined up in 1811. Turns out they weren't. Okay? So the last planetary alignment was actually in 1982. Okay? Not in 1811. When there were, of course, many predictions of earthquakes in California at that time as well, and absolutely nothing happened. And previous peaks, so of course, there are various peaks as a peak associated with the moon and with the other planets, so we're talking about when all of these planets are aligned, but maybe when all but one are aligned, etc. Previous peaks in the gravitational effect, 1803, 1624, 1445, nothing unusual happened on those occasions. Okay? And the reason for this is actually that the moon is more important than all of the other planets. It's smaller, but of course it's closer, and the gravitational attraction goes with r squared, and as a result of that, it matters how close you are to the planet. Okay? So yes, he has this physical model, but it makes no sense how he's implemented it. Right? He's just assuming that the planets were aligned in 1811. Of course, we know when the planets were aligned, and they were last aligned in 1982. This is completely false. That's why there was no hesitation in that ad hoc working group to say that there is no scientific basis for this prediction whatsoever. Not that it made much difference. So, I mean, I think I've emphasized this plenty, but let me emphasize it again. There needs to be a theoretical basis for these kinds of predictions. We need a physical model that makes sense, and then we can start to make a prediction and test our model by making predictions and seeing if the Earth behaves in the way that we would predict. Okay, so what constitutes an earthquake prediction? I predicted a few minutes ago there's going to be a magnitude 8 earthquake next year. Does that constitute an earthquake prediction? I guess it does technically, but it's not particularly useful because we don't know where it's going to be, we don't know when it's going to be, and there's always a magnitude 8 every year. So it's not a particularly useful prediction. So we have to start thinking about being more precise. There will be an earthquake in the first week of May next year. If I was to say there'll be a magnitude 8 in the first week of May, that would actually be saying something. In Los Angeles in the first week of May, in Los Angeles on Wednesday, and the magnitude is going to be greater than 8. Now that's an earthquake prediction that you can test. And we're going to say, what about if I said there's going to be an earthquake in an hour? I can guarantee you there's going to be an earthquake in an hour. If I was to say there's going to be an earthquake in an hour greater than magnitude 7, well, now that's not so likely. Okay, so if I was saying that, we could actually test it. Hopefully you're getting the sense here. So what is it that we need in order to make a prediction useful? We need to know the interval of time when it will occur. We need to know the area where it's going to occur. And we need to know the magnitude range that we're predicting. And then we need to be able to compare the likelihood that this will occur, an event of this magnitude in this location, in this time range, and compare it to just a random chance based on the number of earthquakes we typically have on a given day or a given year or a given week. Okay, so that's what we need in order to make an earthquake prediction useful. Okay, questions? Yeah. So the question of how big does the interval have to be for it to be an accurate prediction? Well, I think the thing to do is to turn the question around. So for you as a consumer of this earthquake prediction, how big does the time range need to be for it to be useful? Okay, so that's kind of where this goes. So everybody thinks that earthquake prediction would be fantastic, right? Earthquake prediction is the solution to the earthquake problem. But when people think like that, they're thinking, well, if I'm told there's going to be an earthquake, I can get out of Dodge City. So what does that mean? Okay, so that means that if you want everybody to get out of the way of the earthquake, you probably need to give them a week's warning. Okay, so this means that so within an hour of wood selling, let's say that somebody was to predict an earthquake beneath Berkeley. Right, this now affects you guys. So what would it need? How certain would you need to be before you would leave Tampa? Let's make it your decision, not the chancellor's decision. Somebody's predicting an earthquake in Berkeley on Thursday of next week. How many of you would leave? So if I told you now there's going to be an earthquake on Thursday, you guys would all leave town. I'm sure I would. Okay, I mean, you can see the point. The issue is how certain people need. It's going to have a negative impact on you, right? If you leave town, maybe we were going to have a midterm next week. Maybe I'm not going to cancel the midterm, but I'm going to tell you that there's going to be an earthquake next Thursday. So if you now leave town in order to follow that recommendation, you're going to miss your midterm. So would you do that? How certain would you need to be before you miss your midterm? You see the point I'm getting at. So it's when people think about earthquake prediction, they think that this is the perfect solution. Actually taking action based on an earthquake prediction has significant negative impacts. And maybe that's fine and that's acceptable if there actually is an earthquake. But you need to be really confident there's going to be an earthquake. Okay? Yeah. Well, but wait a minute. But you're assuming that there are earthquake predictions. Yes. So you're saying if we could predict earthquakes, so I'm not trying to understand the question. So we cannot predict earthquakes. But you're saying if we could predict earthquakes, is there a range before there would be an announcement made? Well, I don't know. I guess there aren't any predictions, right? So I don't think we can't predict. Let's not be confused about this. I'm trying to talk through a thought experiment of what would we need for an earthquake prediction to be useful, but let's not be confused. We can't predict earthquakes. Okay. So the positive impacts of an earthquake prediction are obviously that you could evacuate, and that means that you would not be affected if you wouldn't be in this building when this building collapses, if this building was to collapse. Okay, I think that's very straightforward. What is less straightforward is the broader societal impacts, the negative impacts of people responding to an earthquake prediction. And these are listed down here. Property changes. So let's say that we predict that there's going to be an earthquake in Berkeley next year, so a wider time frame, and we're giving it 1 year ahead of time. But we are absolutely certain, right? Seismologists at UC Berkeley have announced that Berkeley will have an earthquake next year. All right, that's the news headline. Well, what might that do to property values? Property values would probably go down. Okay, that means that the tax revenues would go down for the city of Berkeley. So the city of Berkeley might have some problems. The availability of insurance, you probably wouldn't be able to get earthquake insurance in Berkeley anymore. The availability of mortgages, banks probably would not want to give you a mortgage on a house in Berkeley. Okay, so the value of the property in Berkeley is going to go down even more because people can't get mortgages. So the population movement, maybe some people would leave Berkeley for a year. Maybe some of the professors would leave Berkeley for a year. Maybe a bunch of Berkeley courses would get cancelled. Maybe some of the students would leave Berkeley. Okay. Business, the other ones sort of follow on from this. So you can see the kind of effects of earthquake prediction. So earthquake prediction, even if we could do it, and we cannot, even if we could do it, it does not solve the earthquake problem because of all of these other effects. That's the point I'm trying to go for. Okay? All right. So what I want to do with the rest of today is talk about earthquake precursors, note the question mark. So people do predict earthquakes, and people do claim that they could have predicted earthquakes after an earthquake has occurred because they point to some signal, some observation of some kind, and they say that there's some change in this signal, there's some change in this observable before the earthquake occurred, therefore we could use this to predict future earthquakes. And I just want to run through what some of these are. They're listed over here on this figure over here from your textbook. The seismic P velocity, ground uplift and tilt, radon emission, radon gas emission, change in electrical resistivity of the Earth's surface, and then earthquake activity, so swarms of earthquake events. Okay, so that's the list. So starting at the top, the seismic velocity. So you all know that this is Wallace Creek. What the change in the seismic velocity is about is the idea that if you have some seismic source and some seismic receiver, and energy travels along the fault, along the San Andreas fault, you can measure the seismic velocity of the rock around the San Andreas fault. And people have argued, and of course this is what it looks like in cross-section, the energy dives down, comes up to the station, this is an earthquake at some depth. Of course it could be a man-made source on the surface as well. And people have argued that as you get close to an earthquake, you get cracks opening up. Basically the strain is building up, cracks open up, and as a result of cracks opening up, the seismic velocity changes. Okay? So when you have this signal the first time, maybe it arrives at this time, a little bit later, it arrives later, so the seismic velocity has decreased, and that's because these cracks are opening up. All right, that's the idea. That's the concept. There's a physical model here behind this. The catch with this is that it's very difficult to measure the seismic velocity at different points in time very accurately. So to do this, you would need to have two earthquakes in exactly the same location in order to see a change in the seismic velocity. Okay? So that's the challenge here. There's a physical model here, but the challenge here is how do you measure this change in the velocity? And in fact, people are now beginning to develop ways to do this, not using earthquakes, but using what's called sort of background ambient seismic noise. So there actually are techniques now to start to measure this seismic velocity over time and to see changes. But again, there have not been any evidence of earthquake precursors associated with the change in the seismic velocity. Actually, sorry, I skipped over a key point. If we want to predict earthquakes, we need a precursor. We need to see some observable before the earthquake, but we have to see it before every earthquake. If we want to use it to predict future earthquakes, we need to know that we're going to see it before every earthquake. So a useful precursor for prediction is a precursor that occurs before every earthquake. There are lots of examples of interesting observed signals before one earthquake, but what there are not is a single observable before all earthquakes. All right, so that's the difference. So when people talk about seeing some signals, I'm going to show you an example in a moment, it has to be seen before all earthquakes, and we have not seen that, and that is why we cannot predict earthquakes. Okay, ground uplift and tilt. Here's an example of an interesting observable just before a major earthquake. And this comes from Japan, the Niigata 1964 earthquake. There's a bunch of instruments along the coastline that allowed people to monitor the uplift of the coastline. And over the course of a number of years, this is the data, there was this gradual uplift or substance, depending on exactly where you were, and then there was a sudden change, and then there was an earthquake. And so people got very excited about this. Maybe this was a precursor to the earthquake in 1964, okay? That you're seeing this change in the elevation just before an earthquake, and so you could use it to say something about future earthquakes. It actually turns out now that this data is suspect. So again, this is an observable before one earthquake, and now it turns out that the data is suspect. Another example, a bit closer to home, the Palmdale Bulge in Southern California. There was rapid uplift of this region in 1960, or in 1960. It actually lifted up 35 centimeters. That's a significant increase in elevation over a period of, I think, several months. I didn't write that down here. Over several months. And people got concerned, and this is along the San Andreas Fault. The San Andreas Fault runs right through Palmdale. So people got concerned that this might be the precursor of an earthquake. Nothing happened. There was no earthquake. Okay? People now think that this was probably more likely due to changes in the water table in this particular region, but we don't really know what was the cause of that uplift. Radon gas. This is another one that's popularly been pointed to. And the radon gas is released from many types of different rock. It's a radioactive gas, so relatively easy to detect because you just need a Geiger counter. And it's released from many types of bedrock, and so radon is actually an issue in some places because it gets trapped in people's basements. It's radioactive, so it can be quite hazardous. And there have been many reports of radon increasing prior to various earthquakes, the Kobe earthquake, the L'Aquila earthquake. I'm not talking about the L'Aquila earthquake, but the L'Aquila earthquake in Italy a few years ago now, somebody claimed to see an increase in radon gas just before the earthquake. Okay? So the idea here is that again, the radon is released from the rocks. It works its way up to the surface through fractures. And again, if you start to strain that rock, then maybe you squeeze out the radon gas, so you get an increase in the radon gas. But there's very few measurements. Again, it's the silver bullet question. Yes, some people have argued you see increases in radon gas in some locations before some earthquakes, but not in many locations and not before many earthquakes. So it really doesn't get us very far. Electrical conductivity. The idea here is that when you have granite that is water saturated, so there's water and there's granite, and you start to squeeze it, you change the electrical resistivity. And so the idea here is that you can measure a change in the electrical resistivity of the Earth's crust just before an earthquake occurs. And there are people here in the Bay Area who claim this. The catch is it's very difficult to measure electrical resistivity. Here in the Bay Area, for example, the biggest electromagnetic signal that you see by far happens every day, twice per day. Once in the morning and once late at night. And it's when the BART system turns on and turns off. Okay? Because the BART system, of course, is electric. It's a massive system over a very wide section of the Bay Area, and it has a huge EM signal associated with it. So people argue that there was an EM signal before the Loma Prieta earthquake, and that's widely disputed. And the problem is that there are so many other signals, not just BART, BART's the biggest, but lots of other signals in urban areas. Okay, and then the last one is swarms of local earthquakes, which is probably the one that's been most commonly pointed to, that you see a swarm of events and then you see a bigger event. The Orville Dam is an example from your textbook. It's very close to here, the Orville Dam in the Sierras. And so this is the largest earth-filled dam in North America. It was filled in 1969. When you fill up reservoirs like this, you usually cause earthquakes because you're increasing the load on the Earth's crust, and that causes earthquakes to occur. But there were no earthquakes actually when it was filled up. But then a few years later, in 1975, there was a swarm of seismicity, though the swarm then subsided a month later. A month after that, there was a bigger earthquake, magnitude 4.7, and as Bruce Boltz, the author of your textbook, one of my predecessors here, likes to point out in his textbook, he then said there's a possibility of more events. That's about as solid of a statement as me saying there's going to be a magnitude 8 earthquake next year. Okay? If you're having a swarm of events like this, you can pretty much guarantee there's going to be more events. I can tell you from talking with him personally, he's very proud of the fact that he made this statement, and then there was a magnitude 5.7 at lunchtime on the morning that he'd made this statement. Okay, so that's Bruce's earthquake prediction. He talks about it at length in your textbook. So, I don't mean to diminish this. It is an important thing to state that we know there's a swarm of activity going on, so there is an increased likelihood of a bigger earthquake, and that's what he said, and there was a bigger earthquake. Right? It's a little different to being able to say from nothing there's going to be a magnitude 7 on the Hayward Fault next week. That's very different. Okay, so was this a prediction? Well, not in the sense that we're talking about. A very important success in earthquake prediction comes from China. Haicheng, in February of 1975, they saw an increase in seismic activity, and they predicted an imminent earthquake, and an evacuation of a city was ordered. And 9 hours later, there was a very large magnitude earthquake that destroyed many homes, but there was very little loss of life because they'd evacuated. This is a real success. This is a genuine success. Somebody thought there was going to be a big earthquake, they made an announcement, they evacuated, and they saved thousands of lives as a result of making that prediction. So that is a success. However, then it was followed by a failure, a false alarm. Okay, they predicted 1 year later, or a little more than a year later, another prediction of an imminent earthquake, and evacuation was ordered. People slept in tents for nearly 2 months. Can you imagine? All of Berkeley is going to sleep in a tent for 2 months. I can't imagine that lasting more than a few days. And there was no earthquake. It's China. It's a little different. There was no earthquake. So that was a failure, right? It was a false alarm. They issued a warning that there was no earthquake. Another failure, a missed alarm. This is obviously much more serious. Tangshan, in July 1976, so very close. There was no immediate precursor. There was no evacuation. A big earthquake struck Tangshan, and 250,000 people died. So again, this is to point to the fact that there's no silver bullet. Yes, there was an increase of activity, and people got concerned, and they issued a warning, and then there was a big earthquake. So that was a success. But it's not that there's always a swarm of activity before an earthquake, as demonstrated by Tangshan, and it's not that every time you have a swarm of activity, you have an earthquake, as demonstrated in August of 1976.